Computers. What can't they do? Almost anywhere you look around the modern world, computers will be everywhere, solving any and every problem we can come up with. But is it really true that computers can solve every problem that we can think of? Can computers do everything? To answer this, we first need to define exactly what a computer is, to allow us to give it a rigorous mathematical treatment, to get an answer to this question. The solution to this problem can be found in the work of Alan Turing. He proved that a Turing machine is equivalent to any normal computer, equivalent meaning that anything that can be done with a Turing machine can be done with a computer, and any problem that can be solved with a computer can be solved with a Turing machine. But what exactly is a Turing machine? A Turing machine is a theoretical device, which consists of an infinitely long tape, divided into cells, each of which can store a 1 or a 0, and also a machine head, which can move along the tape, reading data from and writing data to it, and behaving according to an internal set of rules. This internal set of rules is a network of states, each state corresponding to a behavior depending on the inputs. At each time, the machine is in exactly one of its multiple states. For example, this machine has two states, state 1 and state 2, as the start and halt commands are necessary parts of a machine, and so do not count towards the state total. So, if this machine is in state 1, and the value read from the tape is a 0, it will write a 1 over the 0, move right along the tape, and go into state 2. The machine then reads another 0, and is in state 2, so writes a 1, moves left, and goes back into state 1, and so on. Until it reads a 1 in state 2, when it writes a 1, moves right, and halts, with 4 consecutive 1s on the tape. Turing machines allow for the idea of anything a computer can do to be given a formal definition, as Turing machines themselves have a formal definition. This is that a problem can be solved by a computer if and only if there is a Turing machine with fixed inner workings and finite number of states, which can be given a tape with the input in a suitable format, and halt with the tape containing an output in a suitable format. Now we can come back to the original question. Is there anything that a Turing machine cannot do? The answer to this turns out to be yes. An example of a problem that a Turing machine cannot solve is to calculate a function called Radol's sigma function. The definition of this is, for any positive integer n, sigma of n is equal to the largest number of 1s that a Turing machine with n states can write on its tape, then halt, given a blank starting tape. So how do we know that no Turing machine can solve this problem, not even a very complicated machine? Well, let's assume that such a machine did exist, call it the sigma machine, and let's say it has s states for some possibly very large number s. Before we get into the proof, there's a few things to sort out first. Firstly, we need to prove that sigma of n is an increasing function. This means that for any number k, sigma of k is less than sigma of k plus 1. To prove that this is true, take the Turing machine with k states, which will halt with sigma of k 1s on the tape. Now, replace where it says halt with a new state, which when reading a 1 will write a 1, move right and stay in this new state. When reading a 0 will write a 1, move right and then halt. This machine has k plus 1 states, and will write sigma of k 1s on the tape, then go right until it finds a 0, replace it with a 1 and then halt, leaving sigma of k plus 1 1s on the tape. This means that sigma of k plus 1 is at least as large as sigma of k plus 1, meaning that sigma is an increasing function. Secondly, we need to make a Turing machine with k states, which starts with a blank tape and writes k 1s in a row. This is easy enough to make, just by linking up k states, each of which will write 1, move right, and go into the next state along, no matter what they read, with the final state going to halt after moving. Let's call this the writing machine. Thirdly, and finally, we need to know that we can make a machine that replaces k consecutive 1s on the tape with 3k consecutive 1s. It turns out to really not matter what the details of this machine are, only that it exists. This kind of thing is very easy to do on a computer, so such a machine definitely exists. Just as an example, here's a Turing machine that will do it with 4 states, but we can say that this machine uses t states for some t, and call it the tripling machine. Now, we're ready to prove that the sigma machine cannot exist. We're assuming for now that it does exist, and then showing that this leads to a contradiction. We're going to do this by building a bigger machine from the sigma machine. Firstly, we take the writing machine with s plus t states, and then attach this to the tripling machine by replacing the halt of the writing machine with the start of the tripling machine. We then attach this to the start of the sigma machine. The combination of these three machines has s plus t states from the writing machine, t states from the tripling machine, and s states from the sigma machine, for 2s plus 2t states in total. This means that the absolute maximum number of ones that this machine can output, starting from a blank tape, is sigma of 2s plus 2t. That's the definition of the sigma function. However, when run on a blank tape, the writing machine writes s plus t ones, then the tripling machine triples this to 3s plus 3t ones, and finally the sigma machine will write sigma of 3s plus 3t ones on the tape, which is more than a machine with this many states possibly could. This contradiction means that the sigma machine cannot actually exist. The sigma function is called an uncomputable function for this reason. No computer program can ever reliably calculate its output for any input. However, there are only a finite number of Turing machines with a certain number of states, and so if every single one of them can be in turn shown to halt with a certain output, or proven to run forever without halting, then we can in fact work out the value of the sigma function for that input alone. A natural question to ask from this point, remembering that sigma of n is defined to be the largest number of ones that a Turing machine with n states can write on its tape then halt, given a blank starting tape, is what are the values of the sigma function that we know? Well, we know that sigma of 1 equals 1, sigma of 2 equals 4, sigma of 3 equals 6, and sigma of 4 equals 13. At this point, these values don't seem too bad. They aren't too difficult to calculate and have been known for some time. So what about sigma of 5? We do not know its actual value, but it currently stands at either 4098 or more than a billion. There is a machine which writes 4098 ones and then halts, but there are also 42 Turing machines with 5 states called the hardly non-regular machines, and all of these have been run for hundreds of billions of steps without halting, but have not been proven to run forever. And sigma of 6? Well, it's at least 3.5 times 10 to the power of 18, 1267, as a Turing machine which outputs this many ones and then halts has been found, but the current consensus is that the true value will be much larger. One very interesting property of the sigma function is that its output values grow faster than those of any computable function. For any function that could be calculated by a computer, even requiring a huge but finite amount of time or memory, the sigma function will overtake it eventually. How do we know this? A function is computable precisely when there is a Turing machine that computes it. Take the sigma function of more than the number of states in this machine, and you will be able to get bigger outputs. So that's the end of the story, right? We asked if there was something computers couldn't do, and we found something. And it is true that no current computer, not even a fully functional quantum computer, could calculate the output of the sigma function for fairly large inputs. However, there is a tiny possibility that we could, in fact, at some point in the future, get round these issues and go beyond modern computing, solving these problems and more. Enter the Oracle Turing machine. This device is just like a normal Turing machine, except it also has the power to interact with a device called an oracle, a mysterious black box that can decide in a finite and fixed time whether a given normal Turing machine will halt or not. This doesn't cause the contradictions, like when a normal Turing machine tries to calculate the sigma function, as the oracle cannot respond to queries about Oracle Turing machines, which are excluded from the calculation of the sigma function. However, the problems don't completely go away, as all the questions Oracle Turing machines solve about normal Turing machines can just be asked again about Oracle Turing machines. The sigma function could be redefined to include oracles, and then all the same problems arise again. However, if these machines could be made, they would still make the solving of some problems, such as breaking currently unbreakable codes, such as those used in banking, possible to do in reasonable amounts of time. The general consensus is that it is not possible to build an Oracle Turing machine in the real world, as currently the only ideas for building such a machine require time travel in an infinitely large universe, or being able to perfectly represent any real number digitally, both of which are currently considered practically impossible. But science and technology move forwards, and it is possible that one day what is currently uncomputable and impossible will become easy and commonplace. But for now, sigma will remain uncomputable, and forever, whatever technologies we use, computers will not be able to do everything.